process. S is a special name for this. Now we'll call this S transpose because S was the name for eigenvectors. So we have, you know that we'll have this kind of features. Okay, fine. So if we look at this system, it is true only for symmetric cases. It's very reserved for symmetric cases, and I mean just not reserved, but if you see, um, also a fact that they are orthonormalized. I will replace the length. So I will replace the length by finally. So finally we have this that the for orthonormal vectors we could resolve this with S inverse S. Then S could be replaced with transpose with some modification Q. Then complete reversal could be possible, and then we would know that. So Q is the word which is reserved for orthonormal. Otherwise, S is okay for orthonormal, right? So after that inversion, we know something more. We want to explore something more about this, and what that is this. Q is an orthonormal vector. So okay. So we know that this identity is giving me this relation that Q transpose dot Q is I. So it's like getting the Q transpose Q is equal to I. So it's only possible when Q is also Q inverse is also actually the Q transpose. So the cos theta, sin theta, and so finally we have this final vector, and then we see that eigenvector in first column. So we can check inner product, and while actually checking the inner product, we know that you take the, as in you want to check, you can check the orthonormalize. You can first try to orthonormalize it. This would be cos square theta plus sin square theta, and should be giving me 1 back. And this also minus cos theta sin theta will also give me 1 back. So this quantity is also this quantity is also minus giving me 1 back. So unit vector in first column is same as this thing, and I know that at this instance I can think about the making it inverse. So then you check the dot transpose or dot product of a vector with itself will be 1 and with others will be 0. So you see that we are in fact able to do that, and when we are able to do that, such kind of decomposition has got meaning, and it is very special, and because it's like my that matrix is coming from any such vector, any such matrix which is in fact rotates any vector by theta. So it's doing nothing but it's like swinging the matrix by theta degree. So, and what are the best special things that that we can make use of this, right? So let us see what we can do. We have seen when K was special, and when K was special. So K was special. Then we had this kind of decomposition was possible, and when When Q was decomposed possible. So when you know that this was orthonormalized, I could decompose this way. So, uh, so I know that at this time S can be converted into Q, and we'll have Q. So we'll get this system, this diagonalization, which is in terms of eigen vectors. So that's called principal access theorem in mechanics, and this is when I get the capacity to you to choose I xx, I yy, I zz as my own Cartesian system, because we know that what exactly is happening, right? So I have chosen them as this kind of system. So this is principal access theorem. Same theorem you get in mechanics, which is spectral theorem in mathematics. So for symmetric, this K breaks up fantastically, and not just you see that this is also breaking up so fantastically. And illumination, this is LD, LT, and this kind of elimination process also you get. And for same K, you could convert, you could have Q or and this kind of thing orthonormalized, and for same K, you could have this SVD decomposition.